7, writing quadratic equations and functions. So we've been looking at things where we're given a function, draw its graph, or describe the function, or find the vertex, or find the axis of symmetry, or the roots. Now, we're going to be writing those equations given some information. So it's the opposite of what we've been doing. But it's a really good thing to practice to help you focus on what we've been working on in the past few classes. Okay, so we're going to be coming up with ways to write equations and write functions based on some pieces of information. Okay, based on some pieces. There are two forms we looked at. We looked at standard form and we looked at vertex form. There is a third form that's frequently used. It's not really given a name. I have a tendency to call it intercept form or root form, simply because if you take a look at it, it's written in factored form already. So it's obvious what the x-intercepts are. So I call this intercept form or root form. You could call it factored form if you want. There's no real name for it. It doesn't matter. Okay? But it's very useful. So if I knew what the x-intercepts were, say the x-intercepts were 2 and 6, well, that means that's 2 and that's 6 right away. Remember that. How do you find the x-intercepts? If I had something factored like this, wouldn't I just make a t-chart, right? And set them equal to 0? Set this one equal to 0, each of them individually, and solve. This becomes R1. This becomes R2. Well, those are just the roots. So intercept form or root form is really just displaying the roots on the graph. Now, how would I calculate A, though? How may I, or what other piece of information may I need to figure out what A is?
X.
What do you mean X?
Well,
Yes and no. You're like halfway there, Dave. What if I knew the roots? So let's say the roots were 2 and 4, right? I could put a 2 here, and I could put a 4 here. Say those are the x-intercepts. So I'm almost done, but I need A. I can't get A just by knowing X. I need something else. Yeah. So what do I need then? If I need X and Y, I need a coordinate on the curve. So if I knew that the x-intercepts were 2 and 4, let's draw a graph. Okay, say these were the x-intercepts here. And I knew those were the points on the graph, and I had a graph like this. Well, clearly A is going to be positive, I know that, but I don't know much more besides that. Make believe, though, I had this point here. And let's say that this point was like 2.5 comma, good? Negative 5. Okay, 2.5 comma negative 5. Well, this is x comma y. If I've got x and I've got y, the 2.5 goes in for x in both spots. It goes in here for x, and it goes in here for x. And the negative 5 goes in for, y, or f of x. So if you plug the negative 5 here, you plug in 2.5 and 2.5 here, and these 2 and 4 are still there, you could solve for A as the only variable left. And A has got to be positive because it opens up. Okay, because it opens up. So this is the kind of lesson we're going to be looking at here. There's going to be more to it. There's going to be some applications. You're going to find problems like find the maximum area of a certain garden. Those kinds of questions are going to come up, okay, in this section. But this is the general ideas where we're going to start from. Now, I don't know if I want to go over this or not. Example 1 says, find a quadratic equation with roots of quantity 3 plus I over 2 and quantity 3 minus I over 2 that has integral coefficients. So this simply means that A, B, and C have to be whole numbers. Okay, integers, whole numbers and their negatives, really. So let's take a look at this one. The sum of the roots is quite simple. Common denominator means carry it over. Add the numerator. You get 6 plus 0, or just 6. I's cancel, giving you a value of 3 for the sum of roots. And that's really negative b over a. Next, the product of roots. I have to remember to do this, and then FOIL the top. When I FOIL the top, the outer and the inner terms cancel because these are binomial conjugates. So I get 9 minus 3i plus 3i, canceling, and then minus I squared all over 4. Well, 9 minus I squared is really 9 minus negative 1, or 10 over 4, which is 5 halves. So that tells me that the product of roots is 5 halves, which is really C over A. Now it's really important to notice that it's really the ratio of C to A, that's 5 halves, and the ratio of negative B to A, that's 3. So in this case, C could be like 10, and A could be 4. C could be 20, and A could be 8. All of these values all reduce to 5 halves, though. So we don't know what the values are. But if C were 5 and A were 2, that would work. So we could start by picking those values. But it doesn't always work out easily, because then it makes B difficult to figure out what that is. Well, then you have to say, okay, well, A was 2. Since A was 2, if A is 2 here, move the 2 up and divide, that makes B negative 6. So that would work. But there's an easier way to do it. Assume that A is 1 for now. Assume that A is 1. And your function becomes the following. 1x squared. B in this case would then be, let's take a look back up here. Okay, if I assume that A is 1, makes this a 1. So I move the 1 up and divide, it makes B negative 3 in this case. And that makes C, assuming that A is 1 again. Okay, that makes C just equal to C over 1, or 5 halves right there. Well, the problem now is that these are not integer values. So we need to multiply everything by 2. And as a result, we end up getting exactly what we had supposed had we had made those values exact. So had we chosen C to be 5 and A, which was here, to be 2, there's C is 5, A is 2, B ends up being negative 6, which makes sense because when we go back up here, this becomes negative 6 over A, which is 2, so positive 6 over 2, that gives us the 3 for the sum of roots. So this is our function with integer values as coefficients. I could have done this. It could also be, and that works, because those give me the same roots. Nothing's changing here. All I'm changing is the stretchiness of the graph in a sense. Okay, whether the graph stretches up or down, so it's a vertical stretch. So this would just be a steeper graph. This graph would be steeper than this one, but it would have the same roots of the graph. Okay, the same roots. Now in this problem, it's really good to note that the roots are imaginary, so we're not going to really see these roots on the graph, but if we were to set this function equal to 0, it doesn't matter which one of these we use, we get the same roots. But this is the answer we're going to use here, okay, because this is the result we get that has the smallest integer values that we can use. So, example 3 says to find a quadratic function. Find a quadratic function whose minimum value is negative 3. The value. What does that mean again? The y coordinate of the min is negative 3. And whose graph has x-intercepts at 1 and 3. What can I do with the 1 and the 3 from the x-intercepts? Think about that new form of quadratics we looked at yesterday. What was the new form for quadratics from yesterday, Chris? Sorry, I caught you off guard.
If x equals a, quantity x minus r1 times x minus r2.
Okay, now continue. What you were going to say?
You sub in 1 and 3 for r1 and r2.
Yeah, so right away, 1 and 3 are the zeros of the function. They're the x-intercepts. They're the roots of the equation when set to 0. Any of those words are fine. Okay, so I'm going to go ahead and write x minus 1, x minus 3. Now, we've used those, so forget them for a moment. Okay, once you've utilized something, move on to what else is there. So what else is there now? Tori May?
The min.
Yeah, the min. The minimum value. And we know that its y-coordinate is negative 3. That's all we know right now. But there's something else we have to think about. What about the shape of the graph might help me? What about the shape of the graph might help me?
Well, if you between like down or up.
Okay, so it's a min, so it's going this way, right? So A is going to be positive. Really good point to note. This will definitely be positive. We could jot that down, right? A is going to be positive. And then we'll find A to prove that.
Oh wait, I'm sorry. you know that since it's -3, it goes up?
You don't because it goes up because it's a.
And
Where does a min occur? At the bottom of a valley, right?
Okay.
So it's got to open up because the word min only. The -3, it could be a max. If it had been max, it would look like this, and it would open down. So -3 does not have to be a min. Okay, it could be a max, the other problem, and then it would look like that.
So min is like this.
Exactly. So what can I do, and what can I utilize about the shape of the graph to help me to come up with something that might be missing here? Any stab at that? What does a parabola look like? Draw it with your hand. Seriously. Right? Either like this or like this. What do you notice about a parabola? It has, starts with the S. Symmetry. It has symmetry. That helps me a lot here. If these are the roots, I can already go like this. And I could do this in my mind or on the graph. There's the roots, right? -3 is the minimum value. Well, the minimum value is the vertex. It's either here, or maybe it's here, or maybe it's here. I know it's below the axis, or if it were above the axis, it would be a maximum value. The graph either looks like this, it looks like this maybe, or maybe it looks like this, or maybe it's steeper. The steepness is what we're trying to figure out, right? Isn't A the steepness? Remember we talked about A, when A is a fraction, it's wider. When A is a number like 3 or 4, it's steeper. So we're trying to figure out A. In reality, we're trying to figure out the location of the vertex here. We know the value is at -3. What do we know about the midline?
Isn't -3 the y coordinate?
Yeah. So what do we know about the midline? I'm giving scenarios. We know where it is, absolutely. But what about these scenarios do they all have in common?
The x-coordinate is the same.
Yeah, the x-coordinate is the same. So anywhere, no matter where, for this case it is -3. I'm saying generically right now. So, yeah. For any case, guys, no matter what, look, no matter what, wherever this is, it's along the same midline, which we call the axis of symmetry. The axis of symmetry in this case is x equals what? How do you know that?
Because it's not.
Because it's the same distance between like 1 and 3.
Yeah, 1 and 3. What's halfway between 1 and 3? It's 2. So the axis of symmetry is x equals 2. The reason worth I was identifying that is because now we know that that goes right here. Okay? The axis of symmetry always goes in for the x-coordinate of the vertex. So for a problem like this, the tricky part is to realize that you really do have a coordinate. You have the vertex. Although you're only given the y value of -3. You need to determine what the x value is of the vertex. Well, the x value of the vertex is always the same as the axis of symmetry. So think about the average of the roots. Right? If these numbers had been like 2 and 17, you want to find the midpoint, that's tough. Just average them. 2 and 17, that's 19. 19 divided by 2 is 9.5. That's your axis of symmetry. So the average of these two numbers is where you get, average of these two is what gives you the x-coordinate of the vertex. Now that we have the full point for the vertex, how can I figure out what A is? How can I figure out what A is? There's two ways, well, there's one way to do this really, actually. Worth, go ahead.
Well, since you now have a coordinate
Mhm.
to comma -3, you can plug that in for the x and y.
And that leaves only what unknown?
One variable, a.
Very good. I can plug in the -3 for y right here. And we plug in the 2 for x here and here. What do I do after I get A? Do I stop there? I boxed it in to show what A is, but that's not really my answer. What's my actual answer, Dave?
You have to write out the formula.
Yeah, so what is it?
So it'd be y equals 3, parentheses, x minus, x minus 1, and close parentheses, and another parentheses, x minus 3.
Good. Okay, that's our final answer. Remember that you need to write out the function at the end. Don't just stop when you get the value of a. Hey, so the value of a is 3. What does that mean about this graph? What does that mean about this graph? It opens upwards, good, because it's positive. And we said, Arthur earlier said a better be positive. What else do we know about this graph relative to the parent function, x squared, the regular quadratic? What do we know about this graph compared to the regular parent function? Compared to the regular parent function. What does the 3 or the value here indicate about the function? It's what? What do we call it? So what's the word? It's width. Very good. It's width. 3, think about 3 with slope. A slope of 3 means it's a steep slope, doesn't it? So when you see a 3, think of a steep parabola or a very skinny parabola. So this graph is narrower or less wide or skinnier than the parent function would be. If you were to draw y equals x squared on the same graph, okay, so that's our answer right there. Here's our vertex. Here's our roots. Okay, if I were to draw the parent function right here, this would be skinnier. So the parent function would be outside of it. It's a narrow graph. It has a quick or a steep rise. This is important, the actual slope of the graph. You're going to hear more about it in calculus, so I keep emphasizing this. So when you see a 3 as a coefficient for a, think of a steeper graph. If you saw something like 1/3, it would be wider than the parent function. It would be out here. Okay? It would be wider than the parent function. The same rule applies for vertex form for a. The same rule applies for standard form for a. A is always the indicator for the width of the graph and whether it's concave up or concave down. Okay? That's what A will always tell you. For all of the different forms, it's always the same thing. Because I think we keep forgetting that. We've talked about this several times now. Okay, when I don't see any hands, I'm wondering like either people aren't focusing or we need to revisit it. Okay? Example 4 says a rectangular chicken pen is to be constructed alongside a house with 60 meters of fencing. If the house serves as one side of the pen, determine the greatest possible area that you can enclose. Determine the greatest possible area you can enclose. Can I get somebody to help me with the diagram? What would a diagram look like here? So I just want you to draw or tell me what to draw. Georgia, go ahead.
Well, there's the house.
Okay, so here's the house.
Yeah.
Bird's eye view. We're looking down. We're looking down on the house. So the roof comes to a peak right here, right? I'll say that it steeps off here. There's a window on the front there. But we're looking down on the house from above.
So on one side there's like a, yeah,
Which side do you want to pick?
bottom.
Okay. So how many sides of a fence are there?
There's 3
Yeah, why only 3?
because they have
Exactly. What do I label those?
16. So they're both 15. They're all 15. No what?
Variables, come on.
Oh,
What are the variables of the rectangle?
X. Oh,
Either x and y or
or
L and W. Either one.
oh.
It doesn't matter. I'm going to use L and W. Whenever I go to geometry, I want to use the right terms. All right? So that's what we have here. Again, it's really important that when you hear these problems, this is a recurring problem on the SAT. A house serves as one side of the fence. That means just draw 3 sides. Just draw 3 sides. Okay? This kind of a problem in the SAT, we might say like, find the length or find the width. I'm making it much harder. Find the length and width is easy. We're going to find the maximum possible area of this. Okay? So we're going to maximize our function. It's really interesting to do. Let's take a look. We know that there's how much fencing?
60 meters.
So what, you want to say the equation you would get then?
Yeah, W plus L equals 60.
Yeah. Yeah. That's right. Okay, that's definitely right. 2 widths and a length equals 60. It's the amount of fencing we have in length. Now, how do I know that that's a length of fence? Look at your units, everybody. It's in meters, isn't it?
Yeah.
That means that it's a length. If it was meters squared, it's an area. So it's a length for sure. So the two widths plus a length must equal another length or distance. What do I know about the area? What would the area function look like here? Because we want to maximize the area, right? And clearly we can't really do anything with just this equation. One equation, two variables, we can't do anything. So what would the area function look like? What's the area of any rectangle? Everybody.
W times L.
Yeah, LW or WL. Okay. So you really need to stay with me and stop me if you don't get what I'm saying. Because this is a bit intriguing or a little bit, difficult. It's what I was saying yesterday. The next part we want to think about is this. We want to maximize the area. So if I could somehow represent the area with a parabola, I could find the maximum on the vertex. Does that make sense? If I could represent the area, believe it or not, with an equation, which gives me many different areas, I can find the vertex and locate it as a maximum, and then I can look at the y-coordinate to get the max value of the area. I don't care about the x-coordinate. That'll give me either the length or the width, but this wants to find the max area. So we're going to try and write this as a quadratic. But right now there's two variables. Everybody see that?
Yes.
L and W. So we can't do anything yet. But we've got some other condition here. What should we do in that other condition?
Well, you can, I would set L equal to,
So solve for.
solve for L. So
Good.
you have L equals 60 minus 2W.
I'm going to pause you there. Good. Hannah, you want to finish the next part?
And then you just substitute the L in the second equation for 60 minus 2W.
Yeah. Substitution method within a function right now, which is a little bit odd to see because we don't have a number for the area. If we had a number, if we knew the area was 100 meters, we could find out meters squared. We could find out the width by solving the quadratic, right? But we don't know the area. Again, let's say this. We don't know the area. We've done this problem earlier in the year, this exact problem where we knew the area. And you would literally plug in the number for the area, solve for the width, plug that bucket back in up here, and get the length. But we don't know the area. So we think of it as an area function. And this is going to sound weird, but remember how we do f of x? I'm going to rewrite a as a of w, because w is my variable. There's no x here, right? I don't see an x here anywhere, I see w. So I'm going to write it like that. So right now I've got, again, 60 minus 2w and a w. It's my area function. I want to find the maximum of this. So I should probably just put it in standard form and then find the, negative b over 2a and go through the process. Okay, at this point though, if you want to, if it's a word problem like this, I will allow you to graph it. And on your graph you can trace and you can find the max. Or you can press second calc and hit maximum and you can calculate the maximum. So if you want to type this in with an x instead of a w into y1, you can. I'm going to do it by hand.
Y1?
So you can watch. Here, put it into y1 or whatever the first graph is. Clear out whatever's in there, put it in the first graph. And hit zoom 6, please. And you're going to notice something. Okay, it's going to look odd at first. You might have to resize your window. Let me give you a hint. When you graph it, it's not going to be in the window. You're going to see it's going to be off the window. So I would change your window settings. Make the x min 0, because you can't have a negative length. Make the x max, since there's only 60 meters of fencing, the width can't be more than like 45 probably. So let's make the x max 60 just to be careful. If you're doing this on the calculator. Make the y min 0 as well, because we don't want a negative area. And make the y max, this area could be pretty large. So let's make the y max like 600.
It said
X min, yeah, because I did have to be negative.
X min should be 0. Min is 0. Maybe it's in the other order.
Be 60. Y min should be 0. 600.
Because look, your y is 0 has a bunch of negatives.
That is cool.
Go to your window, please. Everybody hit window and change your x min and x maxes. And y min and y max is to what you see
Oh, I
here.
see it now.
Go to the X and then max, and then over.
I'm doing it by hand. I'm doing it by hand also.
Trace. Why is it?
I'm going to write it in standard form.
Oh, I'm tracing. How do you make it not give you like crazy decimals and it gives you actual numbers?
Press second calc. If you're on the calculator and you have your graph up, press second and then hit trace. It's the calc button. And then go to max. And it's going to ask you to hit enter. It's going to ask you to give a guess to the left and a guess to the right. So one, hit enter to the left, go to the right of the max, hit enter, and good, hit enter, and then just hit enter again. Get the exact value.
Nice.
Okay? Now,
15,450.
yeah, I'm gonna show it here. Take a look, folks. If you're doing it by hand, you should be able to do this by hand, by the way. Okay, on the test or on a word problem, you can definitely do it on the calculator, but you really should know how to do this. So find the axis of symmetry, right? To find the vertex, we find the axis of symmetry and then plug it back in. Axis of symmetry is negative b over 2a, which is negative 60 over negative 4, which is 15. So that's the x-coordinate of the vertex, 15. Those on the calculator, didn't you get 15?
Yeah.
For the x-coordinate of the vertex? Now, we want to know what is the value, because we want to know the maximum area. This is the width. Take a look, everybody. Here. This is the independent variable. It represents w. It represents the width. It represents the width. But we want to know what the maximum area is, which is the y-coordinate, so we need to know what this is. So plug 15 back into the function here.
You get 450, is that right?
On the calculator, you should have gotten 450. I'll do it here.
30 times 15.
Let's plug 15 back into the area function.
Or you just do a second y equals.
You could, if you're on the calculator. Yeah. I'm doing my hand.
Alright, just one.
On the calculator, you can go to your table.
What?
Yep, and just go to 15 on the x column and look at the y.
Here, I got you.
I have it.
Why don't you go
Second
me?
tables out.
Why? I calculated.
Oops. I'm doing it by hand for those that want to check. Okay, so there's the answer, 450 at the bottom. When you plug a of 15, you run it through.
Wait.
Okay, the area, so this is saying, here's what you want to write in words. The area, when the width is 15 meters, is 450 square meters. Again, the area, that's what this last line says physically in English. The area, when the width is 15, the area, when the width is 15, is 450 square meters. Okay? That goes in up here, and that's what the value of the max is. So what's the maximum area you can obtain? 450 square meters. Oops. Okay? It's the maximum area. Did we calculate the length anywhere in this problem?
No.
Does it matter?
No.
No, we happen to get the width along the way, which is awesome. And if the widths are 15 and 15, it means the length is 30. Remember the whole thing was 60? Remember the perimeter was 60? So 15 and 15 for the widths means the length is going to be 30. I'm telling you now, you can jot this down. It's true, and you can prove this in calculus when you're a senior. The length will always be half of the available perimeter if you're using 3 sides. It will always work out that way. But you can't just write that on the test if you have this kind of a problem. And it won't be this easy, or it won't be the same exact shape because of that. But if you have a 3-sided perimeter like this, where one of the sides is a house it's adjacent to, the length will always be whatever half of the available fence was. What was the available fence?
60.
The length is 30 in this problem. The widths are both 15. Right? 15 plus 15 plus 30 gives you 60. The length always ends up being, I'm telling you. I know. You can prove it. You can prove it in calculus. You do what's called, you take a derivative and you maximize the function and you solve algebraically for it. It's always, the length is always 1/2 of the available total fencing. It always works out that way.
So you could have just figured it out that way.
I know that because I've proved it using calc. You guys have never proved it before. You need to do this one. Once you do it, you can know that, yeah.
But do I need to prove it when I can just logically prove it?
Oh, no, in real life, you know it now. That's awesome. But if you do it on the test, I want you to show it by hand.
I mean, maybe I did know that. Maybe now I know because then we just solved the problem.
Anyway, let's go to number 5.
You haven't done like 9.
Well, that part does help, doing a lot of problems. But it's more of a matter of proving it algebraically in calc. You literally, the answer you get is area max is occurring when you have the length equal to 1/2 of the available perimeter. That's the
So
answer you
I
get.
can't prove things already, so I
Yes, you
just
can.
do them a lot of
So if
times.
I prove
You
it,
can.
can I
No, you
just say
can't cheat.
A ball is thrown vertically upward
Exactly, a ball is thrown.
with an initial velocity of 12 meters per second.
Your shoes don't match your outfit.
Its height after t seconds is given by h of t, ladies, stop, is equal to v0t minus 4.9t squared. Determine how high the ball goes and after how many seconds this occurs. We're determining how high the ball goes. So we're finding the function's max. Everybody see that this is the same problem? It's the same problem we just did. It says, determine how high the ball goes. So what we're doing is we're finding out the height. And after how long? After how many seconds? That's going to be the location. Remember, the coordinates are th here. Right? T is the x-coordinate. Look at the function up here, everyone. Here's your x-coordinate, right? F of x or h of t. So t is here. So whatever you get for x is your time, because time is the x variable here. Whatever you get for y for the vertex is the height, because height is the y coordinate. So if we want to determine how high it goes, find h, or the y value of the max. If we want to know how long or how many seconds this occurs, find the x value of the max. So that's all we're doing here. Let's plug in our initial velocity of 12 meters per second in for v0. You've seen this before. That should be second nature by now. Some of you have to stop omitting this question on the test. I've asked this kind of question like 4 times this year. Some of you omit it every time.
I think I
It's the easiest one. Look.
No, it's just there's one part of it that I don't. There's one part of it that like I always do.
Trips you
I
up?
just see velocity and I'm like,
Yeah,
I'm
No, I always see like 4 different questions and.
Oh, it's A, B, and C. There's always like 3 parts.
Yeah.
All right. If I want to find the coordinate of the maximum, I put it in standard form. Notice I switch them. Okay?
That's how we normally see it though. That's how
Yeah, it should be in standard form. You should write it. You're always going to see it with v0t minus 4.9t squared here, but switch them this way after. Okay?
so this is mess in your brain?
Sure. So find the axis of symmetry so you can find the x-coordinate of the vertex. As always, this value, okay, the x-coordinate over here, this is the axis of symmetry. So negative b over 2a.
Right.
Find the product in the bottom first. And what do you get?
4.9.
Give me a decimal.
9.8. Negative 9.8.
Oh, I got 29.4.
29.4.
Guys,
It's negative 9.
it's got to be a little bit over 1. It's got to be a little bit over 1.
Oh, I used my calculator.
I think you.
What's 12 over 9.8?
1.22.
Thank you.
Makes a lot more sense.
Come on, folks.
You multiply,
Really?
you get 20.
I didn't multiply it.
Hey, notice, what did I write? I didn't write x equals negative b over 2a, because I don't have x. I have t. Look at the independent variable right here. It's t. So please write t equals. It reminds you that this is the time. The time. So after 1.22 seconds, that's the answer to that part.
What?
Okay, that's also the x coordinate. Tori May.
I got 29.4.
That's what I got.
Guys, come on, seriously. Either put the whole denominator in parentheses or do it in steps.
What did you do?
I don't know how it happened.
Oh, David, we made it so it's negative 12 over 2 times
Yeah.
negative 4.
Negative 12 over 2 is going to give you negative 6. Times this is going to give you around 20 something.
Yeah, that's
Yeah.
it.
You need a parentheses. Come on. You know that by now. Anytime there's a product in a denominator, you need parentheses. Always. Okay, don't forget them, please.
We are.
All right, 1.22 is the time it takes. Now, we want to know what is the max height. We've got the x-coordinate. I should do what to it?
Plug it in.
Plug it in. Plug it in. Plug it in.
12,
Okay, plug it back in and get the height.
22,
So let's find the height at 1.22.
14.64 for 12. 12 times 1.22.
Okay, you plugged it in there. Just give me the answer. I'll trust you guys to do the math right now. You could just type it right in your calculator, or you could make a table and type in 1.22 as the x value and get the y value in the table. Remember how you can type it in?
No, just
I'll tell you what I get. Tell me what you get
I got for
as an answer.
I got 7.34.
That's what I got.
Yeah, I mean,
Is it 3-4?
yeah.
Yeah, 3-4.
Okay. All right, so go ahead and plug in 1.22 either here and here or here and here. I don't care. Either one is fine. Or type it in y1 and go to your table and get the y coordinate. So we go back up here, and that's the answer to how high does the ball go? 7.34 meters. That's also the y coordinate. Isn't this kind of cool how you can see this works now? So why are you doing those max min stuff? This is the reason. So many real life applications. The next one's my favorite. Last one. Imagine you want to make some money and you're a production company that makes video games. You produce them. Okay? But to physically produce the games, it costs you overhead. So you pay for the machinery. There's always an optimal speed, an optimal amount, an optimal amount meaning number of copies, an optimal amount of hours that you should be running your machinery to be more efficient. Because when machinery runs too long, it has a tendency to break. So in engineering, you optimize everything. One of my big things in grad school was studying optimization. So you'd be given like all these crazy scenarios about business cost reductions, about labor rates, and you'd have to apply equations in math and then use calculus and engineering to optimize to get the best scenario. So what we're going to do here is we're going to look at a function that's a cost function. What do you want to do to your cost? Always, if you're a producer, you want your cost to be very low cost, so you make profit. So what do you think we're going to do to the cost function here? We're going to minimize it. Perfect. Make it a min. So the same thing we just did, but take a look. The A value. Is the A value positive now? So the graph's going to open. So it's going to have a min. Not just convenient, it works out that way. It has to. If the cost function had a negative A value, could you get a min? No, because it goes down forever if it opens down. So now we have a graph opening up. Let's go ahead and minimize this. Okay, so we have the value of n, where n is the amount of games in millions, games in millions. So if you get 5 for n, it's 5 million games. And C of n is the company cost in $10,000s of dollars. So if you get 7, it's really 70,000. If you get 8 as your answer for the y coordinate, it's 80,000. Okay, we'll talk about that at the end. So determine the amount of video games that should be produced to minimize the cost. And then find what is the cost. What is that value? So again, find x and y, but in different terms. Okay, so let's draw a quick graph of this. Okay? It's clearly going to be a positive value for n. You can't have a negative amount of video games. And you can't have a negative cost either. So I know I'm going to be in this quadrant. Think about it for a second. Look at where the min is on my graph. If I had been anywhere else, I may have had a min whose x or y values had been negative. You can't have a negative cost. You can't have a negative amount of games. It doesn't make any sense. You have to have some cost. Cost cannot be negative. So in reality, what quadrant am I looking at? Which one?
B.
The first, or one. One.
It was this first.
1, 2, 3, 4. Always start with the positive, and then just go counterclockwise. Make the letter C. Okay?
C for
Calculus.
calculus.
Correct.
Calculator. Coordinate plane. Cartesian. I mean, you pick, right? Think of something to help you remember. Doesn't matter which one. Cartesian's the system. All right, so this is what we're determining. We're determining, remember, that C of n is the y value. Please write this. Please write this. C of n is on the y-axis. N is the x-coordinate. Look at the function up here. This is what tells you. Right here, that function tells you. So that's the y value, and these are the x values in here. So that's what helps me. This tells me the following. When I get a coordinate, this first value here is n, the number of games. This second value here is cost, or c, the amount it cost you. So let's go ahead and figure that out. What should I do with the function? How should I write it to start? Should I leave it the way it is? What should I do? Yeah, put it in standard form. So distribute it out. We're going to have 2.1n squared minus 7.35n plus 9.87. Again, get used to decimals. Get used to it. They're never really whole numbers. Okay, I know we make things easy in high school, but not always the way it works. Negative b over 2a. N equals, right? Negative b over 2a. Negative 7.35 over 2a. What do we get?
4.7.35 over 4.2, I'm pretty sure, right?
That's what I got.
Check. Hey, that one's good. 1.75 is pretty easy.
Great, right? I made the problem up. So, it's not 1.75 games. Games were in what? Games sold in? So 1.75 million games. So if I were to write that, here's what it would look like. Ready? 1 for the full million, and then 1.75 million, that's what that means. It's a million, and then 750,000. 1.75 million games. All right, that's awesome. But what's the cost? What's this minimum cost value in blue here that we need to figure out? Bless you. Somebody who has not answered yet today. How do I find the cost value when I know the amount of games? Answer once already. You did. Say again? Yeah, plug it in for n. Very good. So let's plug it in for n. Remember, we're plugging in the coordinate, not 1.75 million, but the coordinate for n, which was 1.75. Plug it in for n. Make sure you square 1.75 first, then multiply by 2.1. Don't make your calculator make a fool of you.
Yeah, I know if I got it right.
It's true. I always hear the statement, my calculator told me this. But if you put it in wrong, it's not going to come out right. What do you get?
3.43.
Yeah, I got that.
Check. Everybody check. You should be checking on your calculator, not on your iPad.
What did you guys get?
3.43.
It is 3.43.
Yeah.
Now, but the cost, go back to the problem. The cost was in what?
Tens of thousands.
In tens of thousands. Go back up, look here. In $10,000s of dollars. So we have to multiply this by $10,000. Okay, so it's really 3 of these 10,000s, which is 30,000 really. And then 4, 3, 0, 0.
Perfect. That's not per, that's per.
That's actually not bad.
Okay, no, that'd be a pretty minimum cost. What does that turn out to be per game? What's the per game cost? Come on, don't do it the wrong way. Don't divide it the wrong way. Dollars per game. This needs to be your numerator. Dollars per game. Look at your units. This is the numerator. Divide this by this. Again, dollars per game means divide dollars. Divide that by games. Tori May, how many cents per game?
2.
2 cents per game. You get 0.02. Divide 34,300 by 1.75 million. You're going to get 2 cents or 0.02 per game. And that's true. To make those discs, it would cost very little. Overhead is probably on upwards of like 10, 20 cents. What are you paying for when you buy a game?
Like 40.
But what are you physically, why are you paying that? There's a reason.
Yes.
What is it? The programmers. All those engineers that are writing the codes that are using matrices are used to make all video games. Rotational matrices, translational, when you strafe in games, when you turn, it's all on a matrix. That's how it actually works. But those engineers, those guys that are writing those codes, they're getting the money. They're getting that profit. You know, then a lot of the profit goes into like the CEO of EA Sports gets his cut. I mean, everybody takes a piece. Okay? So tonight, here's what you're doing. Okay, tonight, here's what you're doing. There's a lot of problems here. Let's do something actually to make this a little bit simpler. Because what I really want you to watch the video tonight so we can continue with the flipped classroom. Or you know what? What's tomorrow's lesson? How about this? Do this tonight. Do your homework tonight. And tomorrow, it's like a short lesson. It's only like 25 minutes. So we'll do the lesson in class tomorrow. And then you can do the homework in class. And watch the next video the next night maybe. I know I want to go back to the flipped classroom. But if I give you this homework tonight, then we're going to have to do 5, 6 tomorrow in class. And we're going to stay on a regular class model. And I mean,
Can we go back?
most people said to do flipped.
Back to the normal one.
Yeah, the
This
normal
one,
one.
no, this one
Or we
was
should
better.
just not have homework.
We did not yet.
You had no homework last night.
But that was because it's just flip.
But I expected to have homework.
So much better.
Do this tonight, and then we'll figure out tomorrow whether or not we have time for it. If we don't have time for it, then we'll figure it out.
Do that homework.
Do regular homework tonight, 7-7, okay? Regular homework. They're multiples of 4, okay? Use your calculator to help you on the word problems.